Oh, okay. All right. So do everyone here knows Gaussian splatting, or maybe someone doesn't know about it? Okay. So Gaussian splatting is the method to kind of represent the space from different angles. So, for example, we have a space here at the left. So this is some scene, and using Gaussian splatting, we can actually film the scene and later represent it from different point of views. So this is very useful. And Gaussian splatting without rendering looks like this, kind of like this. So we can see here the headphones, the caps and stuff. But this is without the rendering. So it's just how the Gaussians are in reality. So what is Gaussian? So this is the structure close to the shape of the ellipsoid. But usually in other mathematics and statistics is just a probability graph like this. Oh. Okay. So this is kind of intermediate structure between a single point and a full 3D model. So what I mean about this is that we have two methods to usually represent the space, is to kind of look at every point as a independent structure. But this is very costly and it takes a lot of time because we have a lot of points to represent the space efficiently. And also we can just do the 3D model of every object in the scene. But this is also very costly and time consuming because you would have to do this by hand for every scene, for every object. So what we want to use is that we want to use some structure, some object that is unstructured, that is independent of other objects, and that can efficiently represent some space. So Gaussian is a very good choice because it's kind of close to a single point, but it also maps some space. Okay, so in Gaussian, we have a mean point. This is the middle of the Gaussian. And the more you go from the mean point, the less color you would have here, for example. So, yeah. Okay. Yeah, so as I said, Gaussians are have a fairly small amount compared to looking at every point, and they are unstructured. They're convenient to work with because they are independent of each other, and so we can do operations and change them independently. And they are also easy to construct using previous methods. So how do we use Gaussians? Well, first of all, we have to make them. We can initialize them from previous methods called structure from motion. This is when you film the scene from different angles using some camera that is like calibrated with motion. And in previous papers, people learned how to make a point representation of the scene. So the point will actually kind of map the objects in the scene. And we can use those points to initialize Gaussians so that every point in the structure from motion is some Gaussians that have a mean in this point. Okay. After this, Gaussians are kind of don't make anything because they don't represent the scene very good. So we have to train them, we have to manipulate them, change them to make them more fitting to the scene. So we can use that, we can do that by doing gradient descent on every Gaussian and train them while comparing them to the actual image. Okay, yeah, so here we can see the example of 7K iterations of gradient descent versus 30K iterations. All right. So, but that's not all. We have some obstacles while doing this. For example, shapes like this, they are not efficiently mapped by Gaussians. For example, one Gaussian can take only this surface of some shape, and things here and here, they don't have any Gaussians. And another example, one Gaussian can be very large and can overlap the shape incorrectly. Okay, also we have the main bottleneck in the efficiency is its rendering. Rendering takes the most time in our algorithms, and efficient rendering is a must in this example, in this situation. Also, we have to keep in mind that we want to have the less number of Gaussians as possible. Also, yeah, we have under construction and over reconstruction here. So the main solutions to those problems are effective rasterization. This is a kind of rendering using parallelism and shared memory. Also adaptive control during training to keep the number of Gaussians low. Generally, we don't want some Gaussians to do too much, and neither we want some Gaussians to do nothing. It means that we don't want some Gaussians to be overly big, and we don't want some Gaussians to be overly small, so that they're practically not visible to the eye. Also, we don't want some Gaussians to be very bright, because that's not very good. So in adaptive control, we can actually handle under reconstruction and over reconstruction using cloning and splitting of the Gaussians. So for example, if we don't have enough Gaussians here, we will just clone this one. And the second one will naturally during training represent the other space in the structure. And while splitting the big Gaussians, we can maintain the same volume of the Gaussians and kind of make them more fitting to the scene. Okay, so Gaussians, to represent the Gaussian, we need to know his mean, so his the point where he is located. We want to know his shape. So his Gaussians are ellipsoids, and they are represented by covariance matrix, which is just the rotation multiplied by scale. So first we stretch them in other directions by scale, and then we rotate them in the space. So this is just linear algebra here. Also, some Gaussians, well, some structures in some spaces can have different colors from different angles. We also want to do this with Gaussians. So we will use spherical harmonics for this. This is structures here. We can see that for every ball here, there is a different color from different angle. And by using them all together, we can get the color of at different angles for different Gaussians. Also, we need density and opacity of Gaussians. So opacity is just how bright the Gaussian should be. And density is kind of like how much the color affects the scene. Okay. So more about actually training Gaussians. This is just a simple gradient descent algorithm. Firstly, we will start from CFM points, structured from motion points. We will initialize our Gaussians. Then we will start the projection at the point of view. So our Gaussians are initially in 3D space, and we want to have a rendered image from Gaussians, so we need to project them on the 2D screen. So we do projection, then we do tile rasterizer, so just rendering. So then we compare the actual image with what we got with Gaussians. We calculate gradient flow from there and push it back to Gaussians while doing adaptive density control. So here we can see the code. Yeah, while we not converge, we get some camera angle and image. We rasterize the Gaussians, calculate the loss, and do the gradient descent in the function Adam. So we will do the adaptive density control every 100 iterations. So here we go over every Gaussian, and actually we will remove a Gaussian if it's too small, if its opacity is too small, so that it is basically invisible to the eye, or if it's too large, then we will remove this Gaussian. And after this, we need to do this kind of thing. We need to recognize where is the under construction and over reconstruction is. So actually, Gaussians here and there, they tend to have a very big gradient coefficient of movement. So what that means is that we want to move them during gradient descent somewhere, because intuitively it's because the program understands that we have a under or over reconstruction here and there. And for example, here the program wants to move Gaussians in this area. So Gaussians in this close to this area have a very big coefficient of movement. And here also the program wants to move this Gaussian out, so it doesn't have the color there. So if we calculated the movement and it's more than some threshold, then that means that we have to either split this Gaussian or clone this Gaussian. If the size of the Gaussian is more than some threshold, we will split them, and otherwise we will clone them. Okay, so let's talk about the main computational bottleneck is the rasterization. So here is the code for rasterization. Here we will firstly remove all the Gaussians that are outside our point of view. So if we kind of here have so if this is, for example, our camera, and we have a screen like this, so we will move every Gaussian that is outside of this area because we can see them. After this, we will go and transform every Gaussian, so map them, kind of make them 2D on this screen. After this, what they do in their rasterization is they kind of cut the screen into the tiles so that every tile have 16 pixels in width and 16 pixels in height. So we have individual tiles for 16 by 16 pixels. After this, we will go every Gaussian for every tile, and we will see if this Gaussian is inside this tile. So for every tile, we will go over only those Gaussians that are strictly inside in future. So we make a list for every tile of Gaussians that are inside this tile, and for every pixel inside this tile, we will only calculate Gaussians that are inside, that are in the list for this tile. That makes use of the shared memory because we will kind of store all of the Gaussians. We will not make an individual list for every tile, but rather we will push every Gaussian in a big list so that every segment of this list represents some tiles. So for example, every Gaussian inside this segment is the Gaussians that are inside the tile number 3, for example. So this will be all in shared memory, and this means we can go over for the tile 3, we can go over only those segments, only this segment. Okay. And how we actually calculate the color of the point. So for example, this is the camera, and this is the arrow that goes through some pixels here at the screen. Yeah. So this is the pixel that we want to calculate the color of. So we have Gaussians here, for example, here and here. We will go over through those Gaussians in order of the depths. So we will go over Gaussians that are close to the camera first, and after this we will go over Gaussians that are further from the camera after this. And for every Gaussian, we will calculate how the color of this Gaussian affects this pixel. So we go over in the order of the depths because the Gaussians that are closer to the camera, they affect this pixel much more than the Gaussians that are after this. Okay. So that's all. Thank you for listening. If you have any questions. Oh.